here's lesson 4. Now, I had to make sure that I pre-inserted everything I wanted to write on my slides because the smartboard does not love being used as a smartboard. So I know that sometimes it looks overwhelming to look at the slide, but I will talk about everything one piece at a time. The definition of population density is the number of organisms per unit area or volume. So if I look over here, and I'm just going to point with my finger, population density is DP. It is on your data sheet. The number of organisms is N on your data sheet. And because it can be out of area or volume, there are 2 versions of the formula. A for area, V for volume. And so I'm going to show you a little example of both types of calculations you could do. Now, why do we need 2 different versions? Well, some things live on land, area, some things live in the water, volume. So it makes sense that we would measure the space in which they live different ways. So in the first example, you are out in the Sheep River collecting samples, and on the sort of shoreline beside it, in an area that's 10 meters squared, you find 12 insects. Now, how would I find the area of like a rectangular shaped space? Someone will know this. I know you will. How do you find the area of a rectangle? Yep. Length times width, right? You know that. You learned it several grades ago. You might have to calculate the area of a rectangle. You would not have to calculate the area of a tetrahedron or an octagon or a circle. Rectangle or square is the type of area that we calculate. Now, how do you know what units to use? Well, here's the great thing about bio. We use whatever units the question gives us. It's not like chem, where you got to make sure mass is in grams and energy is in joules. No, we're just going to use whatever units the question has given to us. So in this question, the unit for the number of organisms is insects, because that's what I was counting. And the unit for area is meters squared, because that's what they told me. And so I take the number of organisms and divide it by the area. 12 divided by 10. My answer is given in insects per meter squared because those were the units that the question gave me. What you'll see too is if it's a numeric response question, they will tell you the unit at the end. It's like they're telling you what you should be dividing. It's like a little cheat for you. So at the end of numeric response questions, if there's a unit, the unit is indicated because you can't fill it in yourself, right? There's no space for that on numeric response. So if it says blank, 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 insects per meter squared, you'd be like, cool, I'm going to take insects divided by meter squared. It just told me how to do the question. Now, population density is not a number of organisms. So I can have a decimal number. That's a question that comes up. Hey, you can't have 1.2 insects. I could, actually, if I was weird and creepy and I cut one up, but because I'm not measuring the number of organisms here, I'm measuring the density, it's okay to have a decimal. In example number 2, this time, we're still at the Sheep River, but now we're taking a sample of water, so we dip our beaker in. It's a 200 milliliter beaker, made out of plastic, not glass, because we're not foolish. And we find a disgustingly large number, 54 larvae, in this tiny little sample that we've just collected. So I use the same formula, but this time, instead of N over A, I do N over V, because it gave me a volume of water. Meters, kilometers, those things are area. Anything that we're measuring with liters is a volume. There are other units that we could use for area and volume. Those are just the standard ones. And remember, it doesn't actually matter. If you're like, I don't know if that's an area or a volume, it's okay, because you're going to use whatever units the question gave you. In this question, there were 54 larvae and 200 milliliters. So 54 divided by 200 is 0.27 larva per milliliter. I knew that was my units because it's the units the question gave me. Now, does anyone want to ask anything about population density? You can do this math, right? It's just dividing two numbers. You don't even need to change the units. You're just going to make sure you put the right one on top and the other one on the bottom. Now, this is on your data sheet, right? This formula is on your data sheet. It even tells you what N and A and DP stand for on your data sheet. So unlike the Hardy-Weinberg thing where like part of it was there and part of it wasn't, all of these things are there. You just got to put them together the correct way. Now, sometimes when we want to talk about where an organism lives and how many of them there are, it's not enough just to say, well, there's this many per square kilometer, because that might not tell us the whole story. So we got to consider the pattern of distribution that you see within that area or within that volume. So I'm going to show you 3 different patterns that we could use to describe organisms in an area. So in all of these pictures, I've got this square, and then each little picture is supposed to represent an organism. Those are little pictures of moose, and I just copied the same picture over and over again so that there were a bunch of them. The first pattern is called random. When would you see organisms distributed randomly? Well, it's when there are lots of resources. When resources are abundant and the members of the population are not in competition, nor do they need to group together to survive. Generally, this is super rare in nature. It's unlikely that for any large amount of time, resources are going to be abundant, there's no competition, and there's no threat to survival. It might happen, but for most organisms, those 3 things don't happen together, and if they do, it's not for very long. So an example that comes close to that would be in the specific window of the summertime, a moose. They're probably not in a ton of competition. Matings happen, right? They don't need to group together to survive because they're super big and they can defend themselves. There's lots of food because it's summertime. Now this is assuming that it's good summer conditions and like it's rained enough but not too much. So we're always assuming ideal conditions here. And we'll come back to that again in the next lesson, this idea of ideal conditions and how there can be lots of organisms randomly distributed when conditions are ideal. Now the next one, I would say, is the most common one that you would see, and it's called clumped. Members of the population stay really close together, and they gather where food and shelter and water are the most abundant. So, in my little example, I'm referring to the snails that really love natural hot springs. So in my area, notice how instead of them all over the place, like the moose was, I have them clumped in little groups. I actually have the same number of them, but now they're distributed differently. And if I just calculated the density of these 2 populations, I would have gotten the same answer. But clearly, they're not the same, right? Some of them are spread out and some of them are in these little groups. So we would imagine that like right here and right here, that's where one of those hot springs is. And these snails that like the heat and the sulfur that's coming from those natural hot springs are all gathered there because that's where conditions are ideal for them. Now the last distribution pattern, maybe I'll just pause here. I see people writing. I'll just wait a sec. Anyone want to ask anything there? My daughter ate a snail. She thought it was a rock. It's not good that she was going to eat a rock, but when she realized it was a snail, she was horrified. And I said, Alexa, you were going to eat a rock. How is a snail worse? But right? The last distribution pattern is uniform. Uniform, if you look at the word, uni means one, form means form. So uniform is talking about one way. If you play on a team, you probably have a uniform so that you all look the same. It's your team uniform. So in the case of distribution pattern, It means evenly spaced. Everyone's got the same amount of space. Now, usually when we see this type of pattern is in some sort of an artificial population, like an agricultural field, where the farmer has specifically put exactly the same amount of corn or wheat or canola in a given area on his farm. Another one that comes close, it's probably not perfect, but would be something like a bird of prey. So in my example here, those are golden eagles that are defending a territory. Now the eagle does not come out with its little eagle tool belt and its little eagle ruler and be like, no dude, this is the edge of my territory. See, we each get 14 kilometers squared or whatever. But they're pretty good at defending a general area. And so that would be the natural example that comes close. It's probably not perfect, not like in an agricultural field where things really are measured off section by section. But those are some different patterns of distribution. So if we take density and distribution together, we can start to get an idea of how many organisms there are and specifically where are they in the area in which we're counting them. Question.